Cool. So as I was telling the new people, the purpose of Dev Lunches is to try to go fairly deep into a topic that is directly relevant to the work that we do every day. So I prepared, we'll see how, I always think it's only going to take like 20 or 30 minutes for me to get through everything, and it always takes longer. So I prepared some things that show you practically how to do load testing and how to think about scalability. So the first part of this will be kind of a presentation, but these are pretty casual, and the more they get conversational and the more that people share their own experiences or ask questions, I think the more value for everybody on the call. But just to give it a sort of structure, I've prepared a few things here. So the sort of inspiration for this Dev Lunch came from a question that we frequently get, which is, how many users can my app handle, right? And it sounds simple on its surface. The easy answer is it depends, right? Like, it depends on a lot of different factors, but most customers are probably frustrated by that answer, right? So the answer that I like to give is, well, think about it. Not every user of your app is created equal, right? You might have some power user come in, click around the app, do a lot of, heavy computations and things like that. They may do the work of 50 other users, right? And other users may come in, do a couple clicks around in the app, and not really end up doing much of anything, right? So it's not really the number of users, but the amount of activity and the nature of that activity within your app that really matters. And so that'll be sort of like the focus of what we'll talk about here. And by way of illustration of that concept, you can think about, let me share this here. So I was thinking about interesting ways to kind of give you the intuition for thinking about activity in your app, right? So we imagine a future where AI has replaced all coders, and what are you going to do with yourself? You'll go out and you'll start your own little coffee shop, right? So here's the logo for your coffee shop. And your coffee shop will have a counter, and maybe we'll hire a robot barista to handle your customers, right? And can everyone see this okay? Is this showing up all right? Okay.
Yeah.
Beautiful.
Cool. It's beautiful. Yeah, I'm gonna try out my drawing skills here today. And let's say the robot barista, he's pretty consistent. He can handle one customer per minute, right? And pardon my handwriting here. And so we could call that 1 CPM, right? He can handle one customer per minute. And so then you have customers who start to come into your coffee shop, right? So in minute 1, we have a customer come in. He gets served in 1 minute. He walks away happy, right? And then in minute 2, so grab that person, say, okay, they walk away happy. Then in minute 2, another person comes in. They get served in 1 minute. They walk away happy. So if this continues, and they lose their head. So if this continues, right, 1 customer per minute, our robot can keep up with that. But now suppose we have 2 customers come in at the same time, right? What is the service rate going to look like for this person? Well, this person gets served in 1 minute. This person has to wait for a minute while the first person is being served. So they're going to be served after 2 minutes, right? And so this is one of, I think, the core concepts of thinking about the scalability and capacity of your app, is not just how many customers or users or how much activity can be handled at a specific moment in time, right? The ability of your robot to serve 1 person at a time, or whatever it is, but the flow of customers and the flow of activity over time, right? So this is a super simple example. We have 1 person coming in at a time, but suppose we had multiple people coming in at a time. So in minute 1, we have 3 people come in, and we know from our previous example that this person will be served in 1 minute, this person will be served in 2 minutes, and it'll take 3 minutes to serve this person. At a coffee shop, that's probably an acceptable delay, right? Person number 3 might be a little bit miffed that they're not first in line, but 3 minutes is not that long to wait for coffee, right? So then let's say in minute 2, right? Let's tick the timer. This person walks away happy, having been served having been served in 1 minute. These two people move up. Some people lose their heads. And let's say 3 more people come in to the shop, right? So this is a new group of people that came in minute 2. Now, what do our wait times look like, right? We're going to have this person, they've already been waiting 1 minute, so they're going to be served in another minute, so they're waiting 2 minutes, 3 minutes. And then these people who just came in, they're going to have to wait a minimum of 2 minutes because of the 2 people in front of them. So this person will have a wait time of 3 minutes, this person will have a wait time of 4 minutes, and this person will have a wait time of 5 minutes, right? So you start to see it, after the next minute, if another group of 3 people comes in, right? So this person walks away happy, having been served after 2 minutes. This person steps up to the counter. There we go. And then the whole queue moves forward here, right? Now, the new group that came in, so this is group 1 here. This is group 2. This new group of 3 people, we'll add a third, who come in now have a minimum wait time of the total number of people in front of them, right? Which is 5. So this person here is going to be waiting at least 6 minutes to be served, 7 minutes, and 8 minutes. And you can see that the basic concept here is that our robot is not keeping up with the influx of new customers into the coffee shop, right? So this is one of the key words. And if you don't remember anything else from this talk, I would remember this word. The key concept here is the throughput of our robot, its ability to service people as quickly as they're coming in. So this is what's interesting here is we now have a nice long line. The person at the back of the line is going to have to wait up to 8 minutes. This actually may not be a problem for us, right? We do have a bit of a backup, but if 8 more minutes go by and no new people come into our coffee shop, then this line will eventually get shorter and shorter, right? People are going to walk away happy and served by the robot barista, and eventually the line will decrease to 0, and everyone will have received their coffee. And 8 minutes, we may say, is not too long to wait for coffee. 8 minutes is it's a long time relative to other customers, but it is an acceptable amount of time to wait, right? We might also say, well, 8 minutes is not an acceptable amount of time. We don't want anybody waiting more than 5 minutes in a scenario like this, right? So what are our options? Well, we can reprogram our robot or send him to some sort of training program to increase his throughput, right? We could double his throughput from 1 customer per minute to 2 customers per minute. And then in that same scenario we just laid out, he could service all of these people within, say, 4 minutes, right? The other thing that we can do is we can add a second counter here, right? So we can hire a second robot over here, and we can split up the queue of people so that they are serviced twice as fast by 2 robots who, let's say, are capable of doing 1 CPM and 1 CPM. So you add those together, and your total throughput is 2 CPM. So hopefully this starts to give you the intuition of how we think about scaling our applications. It's essentially the same thing, except instead of talking about customers per minute or orders per minute or something like that, we're talking about requests per minute or transactions per minute within our app, right? But the same principle sort of applies in terms of thinking about how we scale it. We can either make our app, our robot, faster, or we can add more copies of our app and our robot to process the queue of incoming requests twice as fast, right? So at this point, one big thing that I've glossed over here, right, going back to the original question of how many users can my app handle, is we're essentially here talking about how many customers can my coffee shop handle, right? But the detail we've glossed over here is that these different customers are going to have different needs. They're not all going to want the same kind of coffee. Some of them may have big orders, some of them may have smaller orders. So there's going to be a variance, right, both in what they are sort of bringing to the counter in terms of their needs, and then there's going to be a resulting variance in how quickly our robot or our coffee shop can service them based on the size and scope of the needs that they are bringing to the counter, right? So we may have said our robot has an efficiency of, one customer per minute on average, or let's call it one order per minute on average, but that's going to vary, right? So let's say this is 1 CPM, or one order per minute. That's going to vary, and it will generally vary along what we call a bell curve distribution, right? So occasionally there's going to be a crazy customer who comes in here with a huge order, and that's going to take us, 5 minutes to handle their order because they want 20 coffees or something ridiculous like that. And then on the other end of the spectrum, we may be able to service some people in a matter of seconds, let's say 5 seconds, right? Because all they want is drip coffee, and our robot turns around, pours the drip coffee in a cup, and there you go. The order is complete. And the majority of people will want an Americano or something special, right? An espresso or something like that. And they'll fall in the middle of the distribution, and they'll take like a minute to service, right? So that kind of gives you an idea of how, depending on the type of application that you have and the nature of the requests, the individual people who are coming into your application, what their needs are and how they are using your software, what they're demanding of your software, your service level will vary, right? From being something that is pretty consistent around like, 1 Americano per minute, or say 5 or 10 drip coffees per minute, to something that's less consistent, where it takes you multiple minutes to prepare a huge order. So there's that level of variance, and then there's also the variance of how many new people are coming into the shop at a given time, right? And it will be essentially random in most applications that you deal with. The number of people coming in, the number of requests coming in, the size and shape of those requests that are coming into your app are going to be essentially random. But what you'll see, like in our coffee shop example, is that over time, there will be trends. So with a coffee shop, you can imagine that around 9 a.m. every day, there's going to be a peak in people coming into the shop, right? That'll fall off. There might be another peak around lunchtime. And then maybe there's another peak right before dinner or after dinner when people come in for dessert coffees or something like that. So this would be a trend, and every day it would be a little bit different, a little bit random, but you could start to plan around these sorts of trends, right? You could say, well, in the morning, we are going to need to have more robots so that our capacity is higher, serving coffee, so that our capacity is higher than the rest of the day. And then we can step that down to, say this is 3 robots, and then midday we can step it down to 2 robots, and by the end of the day, there can only be 1 robot serving our coffee, right? So when we talk about scalability, a lot of the time people think about just scaling up, but scaling works in both directions. You can scale something up, and you can also scale something down. So when I think of scalability, I like to think about right sizing the application, right? And in the, there we go. And in the real world, when you're paying people by the hour to stand behind the counter and serve coffee or something like that, there's a very big difference in cost. With applications, I would say by and large, you figure out what your highest peak is, and you can pretty much just keep your server resources at that level all the time. But there are exceptions to that, and there are situations where it does make sense to either automatically scale up based on trends in usage of your app, and automatically scale back down based on those trends, or to set a schedule like this because for example, if you've built an app that is serving school age students, right? And that most of the time they log in at the very beginning of the school day and traffic falls off towards the end of the school day, then you can say, okay, every morning we're going to scale up the app to serve that extra traffic, and then we're going to scale back down again, right? So think about scalability in terms of right sizing, making larger and making smaller. The other things that we talked about were throughput and capacity, right? So this covers scalability. That was the first half of the Dev Lunch topic, and then from there we can talk about how do we assess the capacity and the scalability of our app using observability tools, and I have a few examples of that, and using load testing tools. But I'm going to pause here and say, first of all, was this a helpful analogy for how apps scale and how throughput works? And do you have any questions to what I've talked about so far and how this relates to applications?
Well, the analogy was great for me. Right? No questions, but the analogy was good.
Awesome. Cool. Something I also like to point out, with a graph like this, right? So let's suppose our capacity is here at, let's say it's 5 orders per minute, just to use our robot analogy, right? So they can handle 5, they can serve up 5 coffees per minute. What I was talking about before is our traffic may be down here. Let's say we're getting 3 orders per minute, and then suddenly, breakfast time comes around and we have a lot of people come into the restaurant. This is not necessarily a failure point yet. We have exceeded our capacity, but if we only exceed our capacity for a short time and it comes back down again to sort of like this baseline here, then all that means is that these people will have slower service, but they will eventually be served, right? And if the service is still fast enough, say less than 10 minutes or less than 5 minutes, then this is not a problem. Like I said, this is not necessarily a failure point. Where the app fails is if this happens and you are over capacity for a sustained period of time, and depending on exactly what your app does and how it's structured and things like that, the amount of time that it takes for the app to fail may vary. But this is what you don't want, is to be over capacity for a sustained amount of time. So when we get into load testing, this is really what we're looking for, is how long can we be over capacity before the app fails, and that helps inform how many server resources we need to put out there. So that was just something else I wanted to call out in this analogy. Yeah, there's a question.
Yeah, well, one thing I was just going to add is, and I think another really important thing that's even more fundamental than that, but on the same tone that William was saying, is even just thinking about how would my app scale, period. So it's one thing if your app, you get a celebrity tweets about your product and then 1 million people hit your app and your app goes down and it breaks. That's annoying. But hey, as long as you're able to quickly get in there and scale it up, it'll be okay. What I've seen before is that moment comes and then the engineering team realizes, oh, in order to scale things up, we need to go build something for a week. Yep. And that is not a place that you want to be in.
Yeah.
You want to have the problem that William just showed. That's sometimes a good problem to have. Of like, oh man, we didn't anticipate the scale. Like, we better scale it up.
Right. Absolutely. Yeah. No, that's a really great point. I'm making the assumption here that you can simply add robots, right? And that the robots are all equivalent. The way that we have architected our Bootstrapper and our Django applications is supposed to work that way. But there are cases where you might build a feature where that replication doesn't actually work for you. I'm trying to think of a good example. This week I had to build a cron job for one of our clients, and we only wanted the cron job to run once. But the way that Elastic Beanstalk works is it installs the cron job on every new application instance. So essentially what was happening is, we'd have 5 robots and they would all be running this background task when we only wanted it to run one time, right? So that's a good example of the kind of thing that Ed is talking about, where in order to scale our application by adding more robots, more servers, we had to write some extra code so that they weren't interfering with each other, right? So I think you want to be careful as you're building your application to make sure that the backend at least is replicable in that way, where if you added additional copies of it, it would increase your capacity without creating those sorts of interference patterns. Go ahead, Jennifer.
So when you're saying that like our backend is like built to do that, is that what, like, when we build a new app in the background and you like do a new you like run that like specific script and it gives you like a new admin and a new models file. Is that what you're talking about?
No, not exactly. What I mean is, if you, even on like your local machine, if you were to open one browser window, or sorry, one terminal, and do manage.py run server there, and then open another terminal window and do manage.py run server over there, those two applications wouldn't interfere with each other. You'd need to choose different port numbers for them. They would
Oh,
interfere.
I see. Okay.
But those two applications wouldn't interfere with each other, and you could theoretically, if your computer has enough resources, you could do twice as much work by running those two separate processes.
Got it. Okay.
They would just share the same database.
Yeah, and then they share the same database. And I won't get too much into scaling databases. That is a whole nother thing. Like to extend our coffee shop metaphor, there's the robot at the counter, but then there's all the materials and there's the stuff behind the counter that actually produces the coffee, and you could kind of think of that as the database in a sense. That's just another level of complexity here that I don't think we need to get into today. But yeah, so when you're building your applications, you do need to consider the ability to replicate them. And by the way, just to throw some more terminology out there, the idea of making the robot faster is typically called scaling vertically. So you're kind of making your robot bigger, beefier, faster, stronger, that sort of thing. And they call that vertical scaling because you're making the thing bigger. The idea of replicating your robots or creating more servers is called horizontal scaling. And I don't know why they chose those particular dimensions, but those are the technical terms that you'll often hear for the different types of scaling. Before I continue, there is one other type of scaling or one other like scaling strategy that I think is worth highlighting. And that's the idea of caching. You'll often hear about caching. In this coffee shop metaphor, I think of that as like setting up a table off to the side that just has a carafe with coffee in it. I'm gonna try to draw that. There we go. With some coffee in it. And this is for all the people who come in who just want a quick cup of coffee, right? And they can go over here, and you don't need to hire another robot to do this. They're just coming in, they're pouring their coffee in a cup themselves, and they get very, very fast service, and they don't have to go up and waste your app's time with their very simple request. So that's sort of the concept of caching, is that you're taking some very common data or common requests, and you're putting them in usually in memory or some sort of rapid cache where it can be very quickly accessed by anybody. So you give people another place to go to get that sort of thing. So I thought that was a nice way of explaining the fundamentals of caching and how that also helps give you more throughput and more scale. So then you can handle more customers who are like that. Cool. So yeah, if there are no more questions about my harebrained coffee shop metaphor here, we can jump over to Heroku. So we have here, so I wanted to share with you some of the tools that we have available for understanding application capacity, and then also scaling out our apps both vertically and horizontally, right? So I think one of our best apps for looking at this right now is Squirrel. And you see that in Heroku, sort of front and center, they give you the key metrics that you need. And here's that throughput metric that I was talking about. This is sort of in my mind, the most important metric to consider when you're thinking about application capacity. And it's measured in RPS. So that's requests per second. In our coffee shop metaphor, that was sort of orders per second. How many cups of coffee per second is our coffee shop serving out there? So this is getting less than one request per second, which is good because we designed it to handle up to 35 requests per second. But just bear in mind that that's averaged over, I think, a 24-hour period here. So if this was one request per second over a 24-hour period, that's 60 requests per minute. Times 60 minutes per hour times 24 hours. That's actually a lot of requests that it's servicing. And I think at peak times in a peak hour, it's doing something like 4,000 to 5,000 requests. This app has 4,000 users in its database. It has a lot of daily active users. I can show you a different dashboard where we're monitoring that. So this is actually a fairly active app. It's not, Facebook level scale by any means, but there are a lot of users using this app, and so I think it's a good example. And then the other metric to look at here is our response time. So again, going back to the coffee shop metaphor, this is like thinking about both how quickly can our robot turn around orders and give people the cup of coffee that they want, but also underload when you do have people coming in and placing orders. How is how is our coffee shop performing and dealing with the variance in the types of orders that are coming in, right? Some of them will take longer, some of them will be faster. So an average response time here of 319 milliseconds, that's about 1/3 of a second. That's pretty good. Some people are waiting longer though. Some people may be waiting 1 to 2 seconds. That's still in the realm of acceptable sometimes, rarely, right? But if this average were to tick up and most people had to wait more than a second to get their responses back, that would be, in my view, an unacceptable response time, right? So we glance at this metric to make sure that it's in the acceptable range, and in this case it is. So it's great. Heroku puts this right up on the front page here next to all of the other summary information, but you can go deeper. And I don't know how many of you, actually, a quick show of hands, like you can click the little raise hand button. How many people have actually spent time on this page, the metrics page in Heroku? There's one. Okay, a few people. Cool. So those are the people to talk to if you have questions about scaling your app and interpreting this data. So really quick, again, this gives you a few more charts that the front page doesn't give you. It gives you major events, and this is nice to say, oh, this is when the dyno was restarted, or this is when a deployment happened, and then quickly glance down to the other charts to see if the response times or other metrics changed significantly after some event happened. So that's what that's useful for. But again, I think the most useful ones are these two charts sort of side by side here. The throughput chart on the bottom, which shows essentially over time when our most active periods were. So you can see here between 6 a.m. and 12 p.m. UTC time, there was a ramp up in traffic and then another ramp up in traffic a couple hours later. Still, if you hover over this on the right-hand side, you see what the requests per second look like in terms of 2xx, which is 200 responses, which are okay responses, and then 3xx, which are redirect responses. There are a lot of redirects happening in this app, which may or may not be a good thing, depending. I think there are a lot of redirects here because, by the way, because that's how we serve certain static files. We redirect to them. But the important metric here is, how many requests per second are we getting? So in this 1 hour period between 9 and 10 UTC, we were getting about 1 request per second. So that's 60 requests per minute times 60 minutes. So it's 3,600 requests, which is what it says there, which is a fairly good number of requests coming in. And then looking up at the chart up above, we can see the distribution of response times. And if you look at the right-hand side, you see the average, the 50th percentile response time, which would be the average response time, right in the middle, is 4 milliseconds. That's really, really, really good. It means half of our responses are going back in 4 milliseconds. And then the 95th and 99th percentile, those are the customers in our coffee shop who were at the back of the line who got unlucky and came in with a big group of other people. So those are the worst response times. They're 247 milliseconds and 607 milliseconds. That's still pretty good for our worst response time. So the longest anyone is really having to wait, the max wait time here was 1 second, which is a long time, but still, well, I mean, it varies over time. In this period, it was 3 seconds, which is not great, but that's the longest any one person had to wait, right? Yeah, so you start to see how how the range of acceptable responses works, right? And you want your longest wait times to still be in an acceptable range. If that's the case, then you're doing well in terms of serving all of your users. So again, I'll pause there. Are there any questions about these metrics or any any additions or alternate ways of explaining this that someone wants to throw out there.
Well,
Michael, go ahead, Perry.
I guess like this is great and all. It shows you that there's a slow response at 6 a.m. Now, how do you figure out what's causing that slow response at 6 a.m.?
I'll dig into that next. Yep, that's a good question.
Yeah, I was just gonna ask what the differences in these specific graphs that Heroku provides on like how they measure the load for the dyno load chart.
Yeah. So the one on the bottom, oh, I don't, honestly, I don't really ever think about this one. Oh, I know it. Okay, I know what that is. So the throughput measurement is how much actual traffic you're getting, right? So like in the coffee shop metaphor, it's like how many people are actually walking through the door at any given time. So that's incoming requests. The response time metric is, given that this many people are sending in requests, how are we doing in terms of responding to them over time? Like how quickly are we servicing those requests? So this is just a raw count of incoming traffic, and then this is a performance metric up here. Does that make more sense, Michael?
Yeah. I'm asking about the dyno load chart on the bottom.
Okay, and then the load is a measure of, I think this is a ratio of how many resources are being used on the dyno, but I'd have to look at that documentation there. But I'm pretty sure that that's what it is. So if you hop back over here, they give you a memory chart. And I guess they don't give you a CPU chart, which is kind of interesting. Normally you get like a CPU usage chart. But I imagine that this is some sort of quantity related to how much memory and CPU is being used on the dyno.
Yeah. I think it's the generalized like view of it is just how hard the machine that Heroku is giving us for that app is working. Just to give like a high level description. Yeah,
it doesn't really seem, it seems to like correspond to our traffic at certain points.
But
So,
it could be like a good spoke test for the CPU usage. Or a proxy for the CPU usage, and a spoke test for like, oh, this machine is working way too hard. So if there's like inefficient code or something that, let's say you have a request that returns an unpaginated response to the UI, and the UI has to iterate over a bunch of objects and kind of like, manipulate the keys and do a bunch of different rendering, formatting on different values. Like usually then you'll see this number go up and spike in those cases.
Yeah, and I think that gets into Perry's question of how do we know what's causing latency, right? And how do we get to the bottom of what is the root cause of things slowing down? Generally, I would say generally speaking, things are going to slow down because you have an excess of activity. But it could be that we see a normal amount of activity, but things are still slowing down because there's a coding issue. Maybe there's some, we're using the Django ORM, and somewhere in there we're retrieving all of the users from the database or something crazy like that. And that was recently introduced in the new code push or something like that. So in those cases, yeah, we could be creating our own load problems through programming errors, essentially. But I would separate that from assessing sort of scalability or capacity over time. And there's sort of like a normal amount of traffic or variance that you expect over a long period of time. And then there are abnormal events like programming errors or just poorly built pieces of code. And I think those kind of fall into two different categories, if that makes sense.
Well, so what if this spike isn't just like bad code, and it's more like, okay, we know that this project is going to have a sale today and that it's going to spike to this point, and so like we want to see like what about that spike. Like it's not just that there's 1,000 people coming, but maybe that there's 1,000 people doing one thing that we could do better. So like, is there a tool that we like? I know Rails had that Skylight or something it was called.
Yep.
That would just track our database transactions and tell us where our inefficient queries are.
Yep. Yes, there are I would say 2 tools that are really easy to use that I would put into all of our apps. The first is the Heroku Postgres add-on itself. It has this dashboard if you click on it, and I don't know how many people have looked at this, but this is pretty useful to kind of see at a glance how many connections you have. Django uses persistent connections, so this will tend not to change over time. The connections will be opened and then they'll stay open. How many commits are being made to the database over time, how often we're hitting cache on indexes. These are a little bit more detailed, but we could talk about that another time. How big your database is and things like that. But to your specific issue, Perry, you can click on this diagnose panel and you can see your most time-consuming, most frequently invoked, and slowest database queries, right? So there's what Michael was highlighting, which is you may have things consuming a lot of CPU or memory, which would be in the Python code, and we'll look at a tool for that in a second. And then there are also just slow queries, and then this, in my experience, is more often the cause of slowdowns or latency for people. Is you have, especially when using Django or an ORM like Django, you have queries that are much bigger than you intended them to be, and therefore much slower. And this is a way to find those queries. In our case, let's see, the slowest query is taking 4 milliseconds. So we're doing pretty well over here. But I do remember there were 1 or 2 really expensive queries in here that we had to optimize. Were people aware of this tool?
Yeah, I think it's a fun also way to see what kind of query does Django do when it actually calls in for something sometimes. Sometimes it'll surprise you when you think it's just going to be a single DB call and then it ends up being something more complicated. Yeah.
I came across, I'll see if I can find this article. I came across an article about sort of the N+1 problem in Django. And a common thing is that you'll have a user here's probably the simple example. Like you have a book and a book has authors, right? So you want to get all of the books, but then you also want to get some information about the author, either the author's name, and then maybe there's a third model that the author is tied to, like their publisher. And so when you do those they're called joins, those join queries where you get the book and then you get the book's authors and then you get the author's publishers or agent or something like that. They stack up very quickly, and then you'll see a lot of join statements in your code like this, and that's usually a sign that your query is likely to start getting inefficient. Cool. So yeah, I love this dashboard because it gives you a quick glance at your most expensive queries. It shows you in SQL and not in Django, so it may require some thought to say, okay, which query is that in Python, in Django, and you'll have to kind of map that back to your code. But it is a really good way of spotting those things from a high level. And then the other tool that I think we should install in all of our apps, it is $50 a month, but it's super useful, is New Relic. And I will try to find a simple example. I will say this about New Relic is it's very overwhelming. Probably the first time you look at this, it makes no sense. And so I want to acknowledge that right up front. But this is a tool that will allow you to dig into the code execution. So I'm sorry, I'm not sharing the dashboard. You're probably like, this doesn't look crazy. Here we go. So here's the New Relic dashboard for the Squirrel app. We're getting some of the same data that we got from the Heroku dashboard, but in greater detail. So we have our throughput down here, and then we have what they call the transaction times. A transaction is a full request and a response. So that's considered in New Relic's terms, that's the entire transaction. So for example, the client requested all of their notifications, that executed the notification view set code, which called the database and ran a specific query, which then responded with the data, which was then serialized and sent back to the client. So that entire request response cycle is a single transaction. And I'm going to try to click down into transactions and show you something interesting. So here we have the most time consuming transaction. It is this GraphQL introspection. I think that this is actually rolling up all of our GraphQL queries into one transaction group, which is not super helpful. It's one of those things that with GraphQL, I get a little annoyed sometimes because at least with RESTful endpoints, you can see them, you can see how often they're requested separately. Whereas with GraphQL, things usually just get grouped under GraphQL. But we can dig in here and we can see that the GraphQL view got called. I know this is kind of small text here. The GraphQL view gets called. Our connection to Scicop G2, which is our connection to the PostgreSQL database, got called. You can see how much time is spent in those things. So we're spending 30% of our time in the GraphQL view. We're spending 11% of our time talking to Postgres. We're spending about 10% of our time resolving the JSON web token, which is actually a really interesting information. This overhead is built into every authenticated request in our app. So we're checking the JSON web token on every request, and it's taking 10% of the request time. That might be, if you wanted to optimize this across the board, you might look into how do we make this go faster across the board. And then it's resolving a timestamp and stuff like that. So let's see. Then you can go even further. So here's a database call where it's selecting a user or it's selecting Hordak. It's arranged by time. Hordak is, by the way, it's an accounting library. It's arranged by percentage of time. So you can quickly find the most time-consuming things and then dig into those and see data about them. I won't spend a lot of time on this because there's a lot going on in here. But if somebody has if you ever come across an issue, a performance issue, and you think that it's because of your Python code or something like that, I would install New Relic, and then you can call me and we can dig through it together because it's sometimes a little difficult to navigate. Go ahead, Perry.
So is there a way here to try and basically simulate requests, or to see what happens if 100 people do something, or do you still have to write those manually and run them, say, on your staging database or something?
There is not a way to simulate requests with New Relic. This is just an analytics tool. But the next thing I'll show, you're like one step ahead of me, Perry. The next thing I'll show is how to actually run a load test, and then you can have New Relic installed and dig into this information from your simulated users. So that is possible. And then you can start to see where things are slow in your simulations. Go ahead, Ed.
One thing I'd say, William, is the next time somebody runs into a problem like that where they end up using New Relic to debug it, it would be great to record that as a loom and drop it in the channel, because then you could quickly see oh, I went here, and then that raised this question, which led me over here, and that's how I found out, oh, it's this one specific call that, because sometimes it can be deceptive. Sometimes the slowest thing is only called once. Yep. And the thing that's actually slowing you down on its face might not look slow, but if you call it 1,000 times, well, then it adds up.
Exactly.
So,
yeah. Actually, that is something that I did troubleshoot with New Relic. I didn't have enough time to prepare a good example of this, but that's a great point. We had this. So on Squirrel, you can take a CSV document, right, a spreadsheet, and you can use that to create a classroom or even a school full of users, right? So some of these schools have 1,000 students, so they'd have a spreadsheet with 1,000 students on it, and they wanted to be able to upload that through the Django admin interface and have all those students be created and all those teachers be created. And that was running very, very slow. It was taking multiple minutes for that to process. And so the Django admin dashboard was timing out. So I started digging into, okay, why why is this happening? And I used New Relic to diagnose it. And I found out, by looking at the transaction and looking at the Python code that was being called, it was spending a ton of time in the make password function, which is a hashing function that's built into Django. And it was spending something like 50% of its time in the make password function, which was a big surprise to me. I didn't think that that function was so slow. And when I dug into it, it's not slow by itself. It takes it's slow for code, right? It takes half a second, but you don't notice that when you just run it one time. You only notice it when you run it 1,000 times for 1,000 users. And then suddenly you're like, oh man, it's taking forever to hash these passwords. So that's a really good example of things that can surprise you, that are scalability issues, that you only really realize when you have to deal with that many users or that many invocations of a particular function. Cool. Yeah, I may have actually made a video of that. If not, at another time, I'll try to record actually diagnosing a problem with New Relic. I think that's a really good thing. Any other questions about New Relic or what it's for? It really centers around, I would say this, it really centers around allowing you to dig into the transactions, and you can, I can't find this view right now, but you can even get a view that shows you the code execution, and shows you every single function that called another function, called another function, called another function, and then went back up the call stack. So I find that really cool. You can see exactly how your code is running in production.
So not to make this about New Relic, this step call, but like if that's the case and this is like pretty useful to us and seems like it could do most of the things that we want, then is it possible to just send all of our logs here instead of through Rollbar, or do we still have to use something like Rollbar?
I think logging is a different use case from this. In my opinion, so there are even two different types of logging, right? There's logging to be alerted about issues as they come up. And by issues, I usually mean uncaught exceptions, or even exceptions that are expected but are happening too frequently. That's what Rollbar is for, from a logging perspective. There's another type of logging, which is logging for debugging, where you are recording things as they happen, but you don't really want to be alerted about them. But you do want those logs there to go look at them if something does happen, and be able to kind of go back through history and see what happened. And then New Relic is in a different zone for me. It's not really a logging software. It's more analytics.
Right, but if so for in mobile, like we also have Sentry installed now to give us crash analytics, and it also does logging, but then we also have Rollbar for logging, and then if we want to install New Relic, that's like a third tool, and they all seem to have the same information. So I was just wondering if there was a way to just basically have merging all these apps into one.
Yeah, I think I think you could try to get by with that, but I think you'd still find yourself missing a certain type of data. So all of these, it is frustrating, I agree, but like Sentry and New Relic are different enough that I would install them both. And then I'd also probably install Papertrail for that debug logging and have all three running. But I don't think I would use both Sentry and Rollbar. I would probably they're close enough to each other that I would choose one or the other.
Okay. Cool. Yeah.
But yeah, my typical like suite of tools is here. Postgres for the database, Heroku Scheduler for background jobs, Memcache for caching. I briefly mentioned caching. I would just go ahead and install the free version of this on most apps, so it's there when you need it. The reason to use Memcache for caching is for horizontal scalability. It becomes a shared cache that no matter how many instances of your app you have, they have one place to put cache. So you want cache, generally speaking, to be shared across all of your app instances. That could be a whole nother topic another day. New Relic, and then Papertrail. And then Rollbar is not showing up here, but Rollbar is also installed. You can see that over here as I flash all of our credentials on the screen. So yeah.
So this is going to be internal.
Yeah, this will be an internal.
And you can see there that he's not horizontally scaled right now. There's one dyno there. That's a 2x web instance.
Yeah, so let me get into, and there's a good reason for that as well. But in this case, that's absolutely right. We created one larger instance rather than having 2 smaller instances. And the reason for that is that our load testing showed that the 1 larger instance performed better than the 2 smaller instances for the same price.
Yeah, I was just calling out that this is the tab where you would do that. This is where you would do some of your basic scaling.
Yep. Yeah, that's actually a great call out. I did want to cover that. You click that little edit button, and so adding more robots is just a matter of doing this, and you decide how much money you want to spend.
And just multiplying the dollar bill sign, right?
Yep. And so that, I mean, that is a good segue into load testing, because simply doing this, does not necessarily give you 20 times the performance, right? It might, depending on how your app is architected and how your users are using things. But the only way you're really going to understand how well your application scales based on adding more resources like this, whether it's literally adding 20 robots or adding bigger, better robots, is by running practical tests and simulations against those different scales of app, and then also observing through metrics and through things like New Relic, observing how your application is running in the real world. And so I really want to emphasize that as we get into talking about the load testing. The simulation is good and oftentimes good enough to give you a baseline, but what you really should be doing is watching how your app is performing in the real world under real load, right? But you may not be at the point yet where you have thousands of requests per second. And so if you wanted to understand what that's going to look like and how many servers or robots you need and how big they need to be, then that's what load testing is for. Go ahead, Ed.
Speaking of, you have a bunch of red alerts there. Did we look at those at all?
Yes, okay, the reason I have a lot of red alerts, oh yeah, this was another thing I wanted to call out as a Heroku feature. So you can set up alert monitoring, and I set up monitoring for when the 95th percentile trips over 1,000 milliseconds for longer than a minute. So when the 95th percentile is longer than 1 second, this is a really low threshold, and I really should bump it up to 1,500 or even 2,000 milliseconds. But that's why there are so many alerts here. It is when the longest requests are going over 1 second. But you can see here, like even in our worst situation where there was one request that lasted 7.5 seconds, and that was honestly probably a Django admin request, not an end user facing request. The 99th percentile response time was still below 1 second. So we're still generally in the acceptable range. Basically, these alerts right now, the way they're set up, are just telling me when there are more than a few people using the app. But yeah, I should raise the threshold because it's too many. That's a really useful feature though. So if I set this to, I'll go ahead and do it now. Response times over 2 seconds for longer than a minute. That would mean that we have a few users who are having to wait an inordinate amount of time, that we don't think is acceptable. And so that would be a trigger, via email to come and see what's going on with our app and do we need to add more resources. All right, let's move on to the last part of this, which is how do you do a load test? So the tool I recommend for this, well, there are multiple tools. There's loader.io, used to be a quick and easy go-to. If you just want to run a quick and easy load test, I would use something like loader.io. There's also k6.io. I think Ed had shared that in CoderZone recently. I have not personally used k6.io, but I've heard
it used to be called Load Impact. You may know it by that name.
Load Impact. Okay. Yeah, it gets rave reviews and is widely, at least from my circles of information, considered to be sort of a go-to cloud-based solution. And then the solution I want to show you today is a programmable solution in Python using Locust. So Locust is, I think, an open source library. It's at least a Python library that you can use. It's self-hosted, self-coded. So I like the DIY aspect of it. I think it's a bit more flexible than the other tools, and I'll show you why in a moment here. So I've created a template for Squirrel, and it would be very easy to duplicate this for your own project. The key here is that in requirements.txt, we're installing Locust. That's the only dependency you need. Well, that in Python, of course. And then we are writing a Locust file. And the Locust file is the file that is executed, that runs the Locust web server, which we'll look at in a second. And this is the part that you can script to do multiple steps, right? So before I look at that script, and then, sorry, by the way, you can deploy this to Heroku. So the last step is then to deploy it to Heroku. Under settings, use the Python build pack here. All of this is written in the README of the repo, by the way. Use the Python build pack, and then you set up a web process that runs Locust, and then you can open the application, and the dashboard looks like this, and you can set up your tests. So we'll do that in a second, but that's generally speaking how Locust works. Before we get into that, I just want to share a little bit about the methodology of designing a load test. So we've talked about, getting the intuition for how an app scales. It's all sort of fundamentally about throughput. It's about how quickly you can respond, but it's also how much traffic is coming in and how quickly can you reduce that queue of incoming traffic. And it's not about the number of users, but it's about exactly what those users are doing. What actions are those users taking specifically with your app? And given how your app works, which of those actions has more or less of an impact on the performance of your application, right? So kind of considering all of those things, I like to run a load test that hits the application with a good number of requests and hits common endpoints in the application. So for the Squirrel application, the common endpoints that I picked out were loading the login page, which is loading the HTML page and all of the JavaScript, sending a login request to the API, so actually saying, I'm going to log in as user X, verifying their token, which then happens frequently behind the scenes after a user is logged in, fetching the user's data, which is a pretty big API request that the app frequently does, and then fetching notifications, which is another big API request that the app frequently does when you're on the dashboard. There are a lot of other API requests that the application does sort of as a normal part of using the app, and there's sort of no end of detail that you can include in your simulation. You can also create a very simple simulation that just calls the API endpoint over and over again, and that can give you useful information. But the thing to think about is, if I'm logging in, that's usually a very small API request, right? I'm sending 2 pieces of data in, a username and a password. It's hitting the database, which is usually indexed by username. And so that's a relatively quick database call. And then it's sending back a very small payload of data saying, yes, you're logged in, here's your token. So that may not be indicative of typical user behavior in your app. And so that's why I like to include a few other actions, especially some of the actions that I know are large and data intensive in my simulation. But this list here is pretty much your best guess, your hypothesis of what the most common API calls or user actions are going to be, and what will therefore make for a good simulation of users in your application. There will never be any perfect simulation. That's why it's a simulation. So, I put a little bit of thought into it, but you get diminishing returns after a certain point, right? So that's the first thing to think about, though, is what behavior are you simulating? And then the second thing to think about, I like to lay out in a table like this, is what scales are you simulating, right? And this is a page, by the way, any of you should have access to. I'll share the link after this call, but this is was for a specific client. So here we are testing 5 different tiers of scale. And before I ran these tests, I had no idea how the app was going to perform at these different tiers, right? All I knew is that I was going to start with a standard size app server and a standard size database, and then slowly increase the number or size or both of my app servers. So the first 3 simulations here were about increasing the standard application server size. So back over on the Heroku dashboard, just changing the size of the app server in Heroku, or changing the number in this case from 1 to 2 and then to 4. And then at tier 4, I switched back to having only one server, but I went from a 1x instance up to a 2x instance. So I doubled the size of the instance. And then at tier 5, I tested with 2x instances, right? I didn't change the size of the database. Postgres is really fast and efficient. And when at the point where you start hitting database scaling issues, you're in a very different tier of application development. So I would say for us, by and large, you probably don't have to worry about scaling your databases. And if you do, there'll probably be a lot of people involved in that conversation. So it wouldn't all fall to you. And then the cost here was mainly for the benefit of the client to see what the difference in cost is. But I think that's also interesting once you get results over here to compare the maximum throughput to the cost. And that's kind of the number that you're optimizing for. What's the most amount of capacity I can get for the lowest cost? So then these other columns over here, I filled in as I ran the tests. And I'll show you how to run a test in a moment. And I added the emojis to indicate which ones passed. So all the green checks were passes, and then which ones were either not really acceptable or total failures. And we only had 2 complete failures. These tests all passed, and so I felt reasonably good about them, that I didn't actually end up running these tests over here because the assumption is that they would pass as well. And we got good enough results, and we hit our targets early enough in the testing process that I felt good saying, you know, we can move ahead with this solution. And the solution I also ultimately chose, which we saw, was the standard 2x tier because it was the cheapest for the highest request per second. And then finally, you want to think about setting those targets that I was just talking about. And so Squirrel had the same question that Wham has right now, which is, how many users can my app support? So I wanted to tell them both, like, well, that's not the right question, but we can also sort of estimate the number of users if you're willing to be sort of flexible about your definition of user, right? And so I did some sort of back of the napkin math here, and I said, the real question is, how many requests per second do you want to be able to support? And then if users are, say, making 12 requests per minute over the course of 5 minutes, then you could expect to have 175 users on the app all at the same time over the course of 5 minutes, and the app should be fine, right? So that was sort of how I answered their question with all the other details that we've talked through here today. So this is, I think, the pre-work to doing a load test. It doesn't have to be this detailed, but at least sitting down and having some idea of this chart of what sizes of app server am I going to test, and having a goal in mind. What does success look like, and when am I not being successful, and when am I being successful in my load test? Predefine those, and then you're ready to run your load test, which we'll show next. Go ahead, Ed.
Yeah, and I'd say for a lot of our projects, it's new clients. We're building something new. A lot of them probably don't know the answers to this kind of question. So I would encourage you to work with your PM. The PMs themselves, they're pretty good at like running that kind of thought experiment of, well, let's assume that this app does start to succeed and the client does start to get users. What is that user behavior probably going to look like? And so you may want to run one test that is just, hey, let's assume, again, somebody posts about it on Twitter and tons of people are rushing to our site just to find out about us. And 98% of those people will hit the page, read a little bit, and then leave, right? And not actually sign up, right? So that's one test you could do to just see, like, hey, how many requests, just hitting the main page, how many requests can that handle? And that kind of tells you something. And then for the rest, like, it could just be, pretend user, you have a bunch of active users and they sign up, they do whatever that main flow is, usually that main critical path that you're building for the client, that main core value that the product is. Well, how many users can log in, do that main thing that we expect the user to do, and then leave? And that would be like another probably important scenario to hit. And if you hit those two main scenarios, then you'll end up with two numbers that I think would then greatly inform your conversation with the client. about like at what point in the distant future will things break, or, and by that for us probably means gets more expensive because the client has to pay for more servers.
Yep, absolutely. Yeah. Yeah, I think talking about like what is the worst case in the near term and what do you anticipate being worst case long term and planning capacity around that. When I set the target here of 35 requests per second, I say in the first line there, this might be overkill, and it absolutely is. We even on even when we have multiple classrooms all logging in at the same time in the morning, which tends to be the pattern of behavior for Squirrel, it doesn't come anywhere close to 35 requests per second. The response times do slow down a little bit, and it's noticeable because of that queuing problem that we talked about before, but they don't ever trip over into the unacceptable range, and we could handle a lot more traffic over the long run, right? And so you could extrapolate from that. You could say, today we have 4,000 users and they are generating at peak times, they're generating 10 to 15 requests per second, right? So theoretically, we could have 8,000 users as long as they're following the same pattern of behavior, which is unlikely. But if they were following the same pattern of behavior, then in theory, we could support 8,000 users. So that sort of answers your question. But yeah, it's the trends over time. It's a requirement, right? And it's, like any other functional requirement when we define features and things like that. So it should be treated as such. Go ahead, Michael.
Yeah, I was just going to say to Ed's point that talking through, basically what the worst case scenario might be, often kind of like functions as a reality check for clients, especially when they're going into their like initial launch and they're like worried about all these things, like, oh, like we have to have this feature, we have to have that feature, think people are going to want this, it has to be, has to be this fast and X, Y, Z. Talking through like some of these numbers kind of, brings it back down to like, all right, like at most you may have 100 users in your first like month. So you're pretty far off from the point where you'll need to even, address any concerns about scalability. And often that can, provide a good, like a good segue into talking about like prioritizing, the roadmap, right? And thinking about like what features are actually important for them to get users and kind of take the heat off of this conversation about like having an entire suite of features before they're able to launch. So it's useful, I think, as a practice, just like for us to go through this for our own like technical, purposes, but also it's good for just to like, bring back the conversation to like the client aspect of this. Yeah, I think like how many users can I support is a frequently asked question, and then a frequent statement I hear is, oh wow, this is in responses, this is becoming very real very quickly. And it's like, well, yeah, you have to, if you want to support a lot of users, you have to have a lot of users, at some point, and how are you going to get them? And so it's a focusing moment for them too, because the best projects that we've ever worked on, in my opinion, are the ones where, we hustled to build good software, but the founder also hustled to bring in a lot of users very quickly. And those are sort of the most fun, being able to run load tests and then, make a stance about how many server resources there need to be, and then bringing in real users and the app works, is really validating and really kind of the fun part of doing all of this. And it's where it's what we do. It's what we build this for, right? Is for the people to use. And so, yeah, like you said, it can be a very focusing moment to say, hey, actually imagine somebody sitting down, not just somebody, but 1,000 people sitting down and using your app. Where are they going to come from? Why are they there? What are they doing? That's really what we're talking about, not just the quantity of them, but the quality of their experience, right? Okay, we got 15 minutes, so that should be enough time to demonstrate a quick load test. I'm going to walk through this locust file very quickly. I would call this like a medium complexity load test. Like I said before, it doesn't have to be this complex. If it's simpler, I probably wouldn't recommend locust for it, because the real advantage of using locust is that you can script it. But if you want to do something a little bit
with a few extra steps, like a little bit more sophisticated than just hitting the login page over and over again, then I think this is a really nice tool for that. So there's some setup at the top. There's a timeout, which I set at 5 seconds. That's, typically a browser times out at 30 seconds. So this is kind of an aggressive timeout. But the timeout means like somebody enters the line, right? They wait for 5 minutes or something like that, or at our coffee shop, and they get bored and they walk away, right? Or they just say, okay, I'm not getting coffee today. So that's what that means. And then there's some other information in here. But the real meat of this is writing tasks, right? So I had those 5 tasks that I outlined in the document, the Notion document, and they were login, verify token, fetch the user, and fetch notifications, right? And so all I've done here is I run these in order, but what I've done here is hit the login page, and then at some point, here it is, here's the mutation to actually log them in. So we log them in, we get their token back, we set that as the token on the class here, so self.token, and then we can use that token down here in future GraphQL calls. And if you're using a RESTful API, it would be the same sort of pattern where you get your API token and then you use the request library, or in this case, self.client.post, to make posts to the API endpoints. So it's a bit like writing unit tests against your own APIs. This is a really short module, and you can see most of it is GraphQL boilerplate. This is just copy pasted out of the JavaScript, I think, on the front end of this particular app. So most of this is just the queries for GraphQL, and then the rest of it is, self.client.post, making these post requests. And then this decorator at task here is provided by Locust to actually turn that function into a task that is run as part of the load test. So what Locust will do is it will take our website user class, and it will create however many number of users we specify, and it will make an instance of this class for each one of those users. And then it will repeatedly run these tasks based on how we've configured them. And Locust has really good documentation, so I won't go into that too much, but basically I've configured these tasks to run every few seconds. So Locust will start at, and this is a typical pattern for load tests, Locust will start at 1 user and start running them and running these tasks repeatedly. Then it will add a second user and run the tasks repeatedly. Then it will add a third, and it will keep ramping up the number of users until it breaks. And then it can continue running the test and just tell you, hey, all these requests are failing, or they're timing out, it's not working. Or it will auto fail the test and say, at such number of users, X number of users, we stopped getting good responses from the server, it broke. So that's how the load test runs. Any questions about all that before I jump over here?
Yeah, I got a question. Did you see if that, actually, Heroku's pricing model is, I guess, pretty static. It's like per month, but I'm just curious about how running the load tests affected pricing for the dynos, especially if you're like spinning them up temporarily to different thresholds for the purposes of the load test, if that had a significant effect on pricing, or if they charge up front, or just something to keep in mind as a part of doing load testing.
Yeah, I mean, I would certainly be careful of I think that's a very good point. So over here in Heroku, it's very easy to hit this edit button and crank this up to 100, and suddenly we could pay $5,000 a month for all of these servers, or crank it up to this, and now we're paying $50,000 a month for all these servers. Obviously we don't want to do that, and so I'd be very careful about what you're cranking this up to, and when you're done with your cancel, and then when you're done with your load tests, making sure that you reset it back to a sensible size, especially if it's a staging environment and we don't need this much capacity. Definitely make sure that you reset it there. So yeah, we're going to cancel that.
I'm pretty sure they don't pre-bill though, Michael. I'm pretty sure it's by hour. So as long as you only leave it up for like an hour or two while you're doing your test, it's going to cost nothing.
Yeah, exactly. That's what I was going to say. Is it's all prorated, so you're only charged for the time that you use.
Nice.
And that's also true on AWS. So the real risk is that you scale it up and then you forget, and then you leave it scaled up for the rest of the month, and that's when we get charged. And that has happened once or twice in the past. Not on Heroku though, but we had a few surprise bills that were much larger than they should have been.
Yeah, just be careful.
Be careful. That's right. Okay, cool. So let's hop over here. This will be just a quick demo. So let's see. The staging environment, I think, is running a standard instance. So we can give it 100 users. The spawn rate is what I was describing before, where it, one new user sort of enters the coffee shop every second. Unlike our coffee shop, they just keep ordering coffees repeatedly. So it's a little bit different from that. We could have them, just for a slower ramp up, we could have them spawn every 2 seconds. So it'll ramp up to 100 users who are repeatedly making those tasks. And then we'll start the locust swarm here. And I like to watch the charts as it comes in. So you can see the number of requests per second starting to increase at the top. We went from 2, now we're making 5 requests per second. Now we're making 8. So that's going to ramp up. And then down at the bottom, we also see our response times, which is predictable because we're not scaled up on staging right now. We see our response time starting to get a little bit out of hand. And now an interesting thing happens where you see our request count dipped because at a certain point, Locust stopped sending requests because it wasn't getting responses. And then those failed requests are resulting in these failures. So that's the red line coming up. And now we're getting as many failures as we are sending requests. And so essentially our load test has failed and our response time has topped out at 5 seconds because that was the timeout that we set. So this app cannot handle those, more than, what do we tap out at? 10 requests per second for a sustained amount of time. So then the pattern that we'd follow here is to stop this test, record these results, and then go back over to Heroku. So let's do that. Go to our staging environment here. Go to our resources, and oh yeah, we're using a mini dyno, so the smallest kind of dyno. So we would change the dyno type, bump it up to a standard, and then rerun the test and see how it does with the same number of resources. So, I mean, we could go ahead and do that. It's fine. So let's do a 1x instance. Okay. All right. So now we bump this up from a mini to a 1x instance. We may need to give it a second to reboot, right? And then we can hop back over to Locust, and we can run a new test. We can run the same test with the same parameters. Like I said, it might be rebooting, so this might let's reset the stats.
An important call out also is you may want to make sure to, depending on the app, to test with and without cache. There are a lot of apps where the app works great as long as the cache is working. And if the cache isn't working, the site can't handle anything. And so you don't want your cache to deceive what your actual load is, because you have to assume, oftentimes with load tests, every request is sort of like a kind of a repeat of another one. And so you can end up always hitting cache, whereas a real user would never hit cache. And so you might want to simulate with that assumption that every request the user is making is a fresh user coming in who's never been there before and is going to miss cache.
Yeah, that's a really good point. And I think in Heroku, you probably, well, if it doesn't break your app, you might want to add like a environment variable that allows you to disable your cache. So I'm not going to reveal the configure bars this time, but for example, I usually have a flag in there that's like use memcached or use rollbar or something like that. So you set that to false, and then that will turn your cache off. Yeah, I think that's a great point. I think we would have to wait a little bit longer for the new dyno to spin up, because it looks like this test went just about as well as the last one. But what you would see are, if you give it enough time, you would see results like the ones in this chart where when we were on the lowest tier, Well, actually, this seems pretty similar, right? When we were on the lowest tier, and I had different parameters for what low load, medium, and high load referred to. It was starting to fail in the medium load, which I think was like 10 to 15 requests per second, but it was doing fine at these higher tiers. Cool. I'll wrap up there. We got 4 more minutes for any parting shots or final questions. I really appreciate everybody coming out and sticking with the presentation, and I hope this was informative and relevant and a good way to explain this. If you have any follow-up questions, feel free to Slack me. Absolutely. So any parting thoughts here?
No, this is really accessible. Thanks, William.
Awesome. Glad to hear it.
Thank you very much.
Thank you.
So
Thank you.
basically, Brenna, I think he's saying that you have a lot of work.
You have a lot of work to do?
Yeah, to answer one question.
I must have done well, yeah, if there are not a lot of questions. Okay, cool. Well, the Slack is always open. And again, appreciate you guys coming out, and I'll talk to you all soon. Have a good afternoon.
Thanks a lot, William.
Bye.
Bye, everyone. Thank you.
Everybody.
Bye.
Bye.
Bye.